Welcome to Sairam Tribali YouTube channel. Let us discuss electrons emission due to a metastable and neutral atoms. It's a continuation of module 1 ionization process. In the previous video we discussed ionization process, how exactly the electrons recombination take place, everything we studied. So in this electrons emission, the atmosphere, there are some elements of our atoms which whose lifetime extend to few seconds. In certain electronic states, such atoms are called metastable atoms. They have a high potential energy. Therefore, metastable atoms are able to ionize neutral particles. It can be represented by the following reaction interaction. One reaction they have given deionization process, right? A plus Bm. A is the atoms to be ionized, right? So this is the equation. Keep it in your mind. Okay, this is the equation. A is the atoms to be ionized, Bm is the metastable particles, and A plus is the positive ions of atom, E negative is the negatively charged electrons, right? So it's a deionization process. So this is the equation, and it's very important for the understanding the concepts in the future. So deionization by attachment, electrons detachment. Okay, deionization in the sense electrons are detachments. I mean dissembling. Electrons can combine with the neutral atoms or molecules to form negative ions in a certain gases. Some of the gases have characteristics that are lacking one or two electrons in their outer surface, known as electronegative gases. Electronegative gases have very high electric strength due to formation of negative ion during the deionization process. The reactions are presented uh, symbolically as this one. Okay, previous one symbolically. A plus Bm is equal to A plus electrons plus B. Townsend current growth equation, current growth in the presence of secondary process, Townsend criterion for breakdown. Why Townsend's theory we'll discuss in the next slides. Okay, we'll discuss entire detailed Townsend's equations and derivations also. We can measure the probability of secondary electrons formation by using Townsend theory. Analyzing the ionization by collision is carried out by the Townsend theory. It is applicable for primary secondary ionization process. Townsend's first ionization coefficient alpha. Alpha is defined as the average number of ionization collision made by an electrons per centimeter travels in the directions of the field. Alpha depends upon the pressure P and electric field volts per centimeter E. And third one is alpha proportional to E by P. Let us consider parallel plate capacitor having gas is a insulating medium and separated by the distance as shown figure. So this is a diagram. Ultraviolet rays is falling into the plates. What happens? The electrons will be recombination take place from cathode to anode or anode to cathode if you pass electricity that is from the battery. See here, if suppose if you give power supply this one, what happens? So the recombination take place. Adjustable HV voltage source will be there, and there is an ammeter which is used to measure the current, and a current limiting resistor for controlling the current of current flowing into the this dielectrics. Ultraviolet light also will be there. So this is the overall explanation for the Thomson's equations. Let's see how the anode to cathode or cathode to anode recombination take place. Anode to cathode recombinations will be taking place. Dx is the distance moved, and d is the total distance, E is electric field, and x is the x is the area. I mean like a distance. Okay, gap arrangement. Let us assume that no electrons are emitted from the cathode. When one electron collides with a neutral particles, a positive ions and then electrons are formed. This is called as ionization collision. Let alpha be the average number of ionization collision made by an electrons per centimeter. Distance travel in the direction of the field. Alpha depends upon the gas pressure P and E by P and is called Townsend's first ionization coefficient. So Based on that, the curve has three regions: ohmic region, saturation region, and then Townsend region. See, this is ohmic region, okay? Ohmic region, and this one is a saturation region. Saturation, see, straight line will be there, and this one is a non-saturated sustained discharge, or the Townsend's discharge origin this one, and self-sustained discharge is this one. So once again, I'll tell you, very important for the explanation in the next slides, as well as derivation. Ohmic region, resistive region, saturation region. It's a normally it's a normal constant region. Thousand discharge region, discharging region for reason for the this one derivation. It is observed that, okay, it is observed that from the figure that the current at a first increases proportionally with the increase in the field, okay, or voltage. That's a this one ohmic region, okay. This region is called as ohm. Slowly it is growing, and after that the state situation comes when the current becomes constant, uh, 10. Even if voltage increased, the constant current 10 is I naught is called as a saturation current, not 10, okay. This is I naught. At a still higher voltage, the current increases exponentially. So exponentially this increases. So the exponential increases the current due to ionization of gas by electrons, collisions with the gas molecules. As the voltage increases, electric field intensity volts per distance between the two electrodes, two plates, increases, and hence the electrons are agitated more and more, and electrons get higher kinetic energy, and therefore knock out more and more electrons at any distance x from the cathode. Let the number of electrons be in x, where nx is electrons travels further distance dx. They give rise to alpha in x or dx. Thomson's second ionization coefficient. The single avalanche process described the previous section becomes complete when the initial set of electrons reaches the anode. The probability amplification of the electrons being released in the gap by other mechanisms increases, and these new electrons creates further avalanches. The other mechanisms are, let's see, other mechanisms: breakdown of in electronegative gases. Electronegative gases are the gases that have similarly towards electrons. When electrons comes into contact with these gas molecules, the gas molecules attract the electrons and becomes negative ions. The gases which are lacking in one or two electrons in their outer shell are known as electronegative gases. Okay, next we have a time lag of breakdown. Theoretically, the mechanisms of spark breakdown is considered as a function of ionization process under the uniform field conditions. In a practical engineering design, the breakdown due to rapidly changing voltage or impulse voltage is a greater importance. Statistical time lags, TS, is defined as the time lapse between the application of voltage sufficient to cause a breakdown, and the appearance initiating electrons is called as a statistical time lag, TS. Okay, the statistical time lag depends upon the amount of pre-ionization present in the gap. This in turn depends on the size of the gap and the quantity of radiation that produces the primary electrons. The techniques generally used for the irradiating the gaps includes ultraviolet radiation, radioactive materials, and light sources. Right. So formative time lags, TF, after the appearance of electrons and the time of TF required for the ionization process to develop fully to cause to the breakdown of gap is called as a formative time lag, TF. The formative time lag depends upon mostly on the mechanism of avalanche growth in the gap. Total time lag is defined as the sum of the total statistical time lag and the formative time lag. T is equal to TS plus TF. Okay, TS plus TF we need to add, right? So So this is a diagram for TS plus TF, right? This one is TS, this one is TF, total T. So voltage collapse is this one. This is time taken. This is voltage, right? This is how we are going to represent this theory. So streamer 3 breakdown, gas avalanche breakdown will be there. In the next class we'll discuss.